extra strong Roman concrete,
fully hydraulic,
natural solid connections.
It's the
Structural engineering podcast.
Hey, and welcome to this week's episode of the Structural Engineering Podcast. My name is Max,
And I'm Zach.
and this week's episode is going to blow you away. What are we talking about this week, Zach?
Oh, we're talking wind loading.
Nice thing about wind, unlike seismic, is it's everywhere. Can't move to Nebraska and hide from it. It's there.
That is a good point. It's definitely a different lateral load, but it's a totally different way that it is applied. You know, seismic is being ground motion and wind being a fluid pressure up against our structures. I think it'll be interesting to dive into wind loading and learn a little bit more. How about this week, before we dive into that, we follow up on some quick news.
Yeah. What do you got?
So I just saw the Salesforce Transit Center. You know, we talked before about big plate girder that had failed.
Crack in there, right?
Oh, yeah.
Bottom
Big
flange crack.
bottom flange crack of the 4-inch built up section, an I-shaped section that was tapered. The flanges were 4 inches thick. Well, they've come to a conclusion of what it was, and it turned out it is actually an error on the fabricator's part of things. I believe what it was saying is they torched the hole into the plate, and then they didn't grind it smooth, and there was this whole process that created the failure of like the middle part of the plate became very brittle, and due to the loading of the structure, as it was opened, it created that fracture. So I think
that's crazy.
It's pretty crazy to see how fast they got
fracture grew, or the
how
fact
fast
that how they figured it out.
Yeah, both of those. I think it's pretty crazy. You know, you look at the bridge in Florida that collapsed, and that's taken a lot longer to really get to what happened than this. And you know, sure, there's a lot of different other factors that were going on with the bridge in Florida, and some new systems that were being used that might, you know, be adding to this delay of understanding fully. But I think it's pretty cool in the Salesforce Transit Center that they kind of kept people up to date. And
absolutely.
I believe this news came out of the steel conference that happened last week in St. Louis.
Ah, cool. I imagine that engineer is a great sigh of relief, but man, I feel bad for everyone in that situation. If it's on the fabricator, that's just a bummer all around.
Yeah, absolutely. It's definitely good lessons learned for that industry.
I wonder, I remember when we were talking about this the first time, we mentioned that the detail, was nobody thought it was a good detail. People, that review this type of thing, not us, we don't know, but people that are professional in this sort of detailing said this is just not a great way to route your loads. I wonder if he had done it somehow a little bit better, if the fatigue never would have, propagated, but the micro cracks.
Right. Yeah. And it's just crazy to think that the way they found this issue was due to the fireproofing being cracked. I mean, that's just crazy.
Yeah. It could have been catastrophic pretty easily.
So yeah, that's the news this week. Something else that's going on that's really cool is the Tall Building Council is meeting in China right now. And so I believe there should be some pretty cool news next week. Next episode.
See what comes out of that. How about this for a segue?
Let's get windy.
There's wind in China. Speaking of which.
Wow.
Yeah, that's as good as I have.
Mind blown.
Where does wind come from? What is this thing? Let's start at the bottom. Exactly. It's from people breathing across the world. No,
I believe winds were developed by the International Building Code.
Really?
Yeah, I believe it's
just
a
give
conspiracy.
you something to do when there wasn't an earthquake.
They got jealous of earthquake loading and they wanted something else.
Well, I got a better answer. I'm going to give you the sun.
Hit me with your best shot.
Oh, that's it. The sun. That was as good as it gets. So ultimately, wind comes from uneven loading, heating, I guess, heat loading of the Earth. Right.
What about black holes?
Hot topic, but not helping us right now. Not important to this. Yeah. So basically, Earth spins around, and heats some areas of the Earth's surface more. Albedo or something like this. I haven't used that word in a while. basically how much heat a surface takes in. And so,
Yeah.
a black surface takes in more heat than a white surface. So due to that uneven heating, there have high pressures and low pressures. And the same, that sort of creates storm cycles. I obviously don't know really what I'm talking about. This is not structural engineering, but I read it. So
On the internet?
it was a book. It was a textbook. So the wind wants to move from the higher pressure area to the lower pressure area, and it's just a constant cycle. And there's sort of a dominant wind in the northern hemisphere. It goes from the west side to the east side, heading slightly south.
So I think to summarize that, the sun heats the air, and then hot air rises, cool air moves in to fill the space, and then thus moving air is wind.
Let's go with that.
And let's call that the wind cycle.
Let's call it the wind cycle. What about the wind scale?
Now you've lost me.
There was a guy, Sir Francis Beaufort, in 1805 that had nothing better to do but to break wind speeds up into little categories and formally make a wind scale, the Beaufort wind scale, or Beaufort. This is, sort of comparable to, I'm going to say the Mercalli. It has nothing to do with damage. It only has to do with wind speed. So yeah, he's got the scale, and he broke it up into, I don't know, it looks like almost a dozen categories here. And they have nice words like strong breeze is 22 to 27 knots. It starts with a gentle breeze. It moves to a moderate breeze. It gets into a gale, a strong gale. It goes on and on. They're very non-descriptive. But this is the formal scale. This is the formal wind measuring scale. And anything over, so you end on hurricane. It goes violent storm, hurricane, and then anything more than that, that's just too fast.
Do you know what knot conversion is to miles per hour?
No idea.
1 knot is equal to 1.15 miles an hour.
What's a knot?
So have you ever tied your shoes?
Okay. Hey, how fast
can
wind
nautical
go?
mile? It's a nautical mile per hour.
What's the fastest wind you've seen?
270.
You were there?
I was there.
Come on.
I was dreaming.
270's got to be a tornado, though, right?
Yeah, absolutely. Hey, that's a whole nother topic we go over. The FEMA 500.
The storm shelters.
Oh yeah.
I found, so I think on the East Coast at least, I grew up being told that Mount Washington was the windiest place on Earth because it's, cool. And they had a wind speed of 231 miles an hour recorded in 1934.
Wow. So
it is no longer the fastest ground wind speed non-tornado. That was beat in, 2005 or something? 253 miles an hour in Australia.
My goodness.
Yeah. Let's see. So we're in a pretty windy region here, the Front Range of Colorado. What sort of wind speeds do we deal with on a normal basis?
I would say probably somewhere around 140.
140, yeah, and that'd be getting up there, but we definitely have 140 on the Front Range, and then heading into the mountains, I think 180. I think Estes is 180, a little town in the hills up here. So when we're looking at these wind speeds, we get from the code, we pull this 140, 180, down. Really in our town, we're looking at 115 to 130. Where does that wind speed come from? Who decides that is the speed that we're going to design for? Because obviously, if you go out to Mount Washington, I don't think they're going to tell you that the design wind speed is 231 miles an hour.
Yeah, it's based off of a committee that decides an occurrence. I would guess.
You would know. You would know. Yeah, you're right on. It's some heavy statistics, I have a hunch, but based on the data that they have, and this has changed a lot. I don't want to jump around too much here, but right now we look at a 3-second gust, but we used to look at something that was just fastest mile. The weather stations kind of stopped recording fastest mile in a sense, and they changed over to this 3-second gust sort of recording. So the building code had to follow the available data. So now we're in this 3-second gust sort of deal. And the way they decide how much, what is the wind speed that we need to design for is by deciding what mean recurrence interval is most appropriate for the building type. So this is all about like the reliability of the building. Basically, like when we're talking about seismic, the chance that it falls down. What wind speed do we have to design to that are the probability of this building falling down is within our standards. So when we're looking right now, in ASCE 710, if that's what you were working with, and beyond that. Pretty sure I haven't double checked this one, but if you go into ASCE 716, you're looking at a 3,000 year mean recurrence interval. So what this means is that looking at a 700 year MRI, which is for a risk category 2 building, there is a 0.14% probability that that event will happen every single year. This is the same as you would see like a 100-year flood you'd hear on the news. And you could have multiple 100-year floods, back to back. Just means there's a 1 in 100 chance that that's going to occur in a given year. Yeah, so we've got, looking at what we designed for, a 300-year MRI when we're looking at risk category 1 buildings. So these are your barns and whatnot. Moving to risk category 2, like I said, we're at 700. And then in ASCE 710, risk category 3 and 4 are combined, and that's a 1,700-year mean recurrence interval, which is a very long time.
That's what I want all my buildings designed to.
Coming right up. Easy. But these wind speeds are not dramatically different, right? If you're jumping from, you can kind of compare it to the old ASCE 705 where we still used importance factors. The numbers are pretty comparable. You're looking at maybe a 10% difference between risk categories.
Well, now that we have a good understanding of where winds come from and a little bit about the speeds of wind, I guess the next thing that we can really go into is where do our pressures come from? What codes are we looking at? Where in the codes are we getting these pressures from? And then, what factors? What are the big things I need to look at and need to understand for my wind loading?
If we look at the wind pressure is probably the next place to start. And we're kind of skipping around the different procedures that you have for analyzing a building for wind pressures. And I think that we're going to do a back-to-back podcast here and get into some examples of some of these procedures. There are more or less 5 in ASCE 710 and 3 in ASCE 705, but we'll get to those later. But either way, we've got a pressure, and our pressure is proportional to the square of the velocity, no matter how you're looking at this, right? So if we were in ASCE 705, our velocity pressure, which we evaluate at our mean roof height, is equal to a constant. So in our case, it's 0.00256 times a couple factors, kz, kzt, kd, v squared, and I, right? So in 705, we still had that I that we just mentioned, where instead of adjusting for our mean recurrence interval, we just forced that value to be 10% higher, 10% lower. But yeah, so looking at 705, when we move to 7010, we lose the importance factor, but it's the exact same equation. We've got the same equation, just no importance factor. And instead, we adjusted with our new wind speed maps. So we have the same 0.00256 and all these K values. So our KZ is a velocity pressure exposure coefficient. Our KZT is a topographic factor, and our KD is a wind directionality factor. We've also got a couple other that aren't built into this equation. One of them that comes to mind is called elevation factor, or the altitude adjustment factor. This is kind of a new one, right?
This is something that ASCE 716 has now adopted It's now fully codified. It is no longer in the commentary in which it was for ASCE 710, and now fully acceptable. I believe before people were using it, the city of Denver would allow up to a 13 or 14% reduction in wind density as that was amended to their code.
Yeah, which is nice. Yeah, what is it? The back of the code, the commentary basically stated that you needed some sort of evidence, and it is sort of vague what that evidence is.
Engineering judgment.
Yeah, I guess so. I mean, I don't know anything about wind density. I think that just gave you the wiggle room if you were doing a skyscraper or something, whatever, a 40, 60 story building, that maybe required, maybe you didn't want to go into wind tunnel testing, but you did want to evaluate this and save some costs, not use the absolute, most wind pressure that it might see. You would deal with this altitude adjustment factor. Definitely people used it for all sorts of stuff. I know some residential engineers that used it all the time, no matter what, which I don't know if that's how you're supposed to do that. But
I think it's just, and if you look at it now, it's fully codified. So.
Yeah, now it's justified. Absolutely. So, now we've got to give you an example. So we're Colorado on the Front Range. We're about 5,000 feet. So our elevation adjustment factor is 0.83. And that's in ASCE 716. In 710, it was tabulated, not codified, and that at that point it was 0.86. So it's actually even gone down a little bit. So we're allowed basically to reduce our wind pressure by that 17%.
And that's something, I coming from sea level more or less. Portland is at like 300 feet. Never even thought about.
Yeah, I mean it's a giant reduction, but it makes sense. Air's thinner up here, right? And that's really what this is about, is that the air is generally colder, so it's less dense. And because there's lower atmospheric pressure, it's less dense there as well.
What's
So
that equation? Chemistry, PV equals nRT.
Yeah, that's the one. I don't know if that applies, but that's an
Well, there's
equation.
pressure in there, temperature. Okay,
Um,
so where in these codes, kind of taking a step back, we jumped right in. Where would I find these wind loads? Let's say I just graduated college. Someone told me to go get the wind loads for this building. Go figure them out. What do I do?
and I feel like I should learn that I need to memorize the chapters when I'm talking to you. It's approximately 3/4 of the way through ASC 7, and if I flip my book, it usually falls roughly in the wind chapter.
Yeah. So wind starts the chapter 26, ASC 7. That's where you find your kind of your general items. They go through definitions of terminology, wind terminology, and then talk a little bit about pressures and all the things that you just discussed.
Mm-hmm.
And then it goes into 2027 and so on for each different procedure. And then the reason we get allowed to use ASC 7 is it's stated in chapter 6, chapter 16, 1609, to be specific, of the IBC. It states you can determine your wind loads based off of ASC 7 and it even states in that chapter 26 to 30. So, that's your basis.
That's your permission.
Your permission to, the IBC gives you your permission to use ASC 7. And so this is, more or less where the code language is to do that. And then now we, kind of continue through going into the wind loads here.
Let's say I want to hit back on one thing on the velocity pressure before we move forward. I said that it is proportional to the square of the velocity. And I think this is kind of it's an easy concept, but you can forget. Let's say you're looking at a building that was in an old code and it had a wind speed of whatever, 115 ultimate. And now it goes up to 125 ultimate. It is not 125 over 115th worse. It is the square of those things worse. So it's much worse than it looks, I guess.
Right.
So, it certainly makes sense. But I think when I was starting out, I just thought of these things as linear, but they're not. So just be aware, I guess.
So the first thing you do, I mean, really with any building, is kind of understand, and you talked about this with the mean recurrence interval. That's based off your risk of your structure, and instead of having an I value, you have these different wind speeds, which kind of come out to being the same thing. Mm-hmm. So now I've got my 3-second gust at a certain altitude. I'm guessing that that my basic wind speed is, a 3-second gust. And then the next thing I'm probably going to be looking for is what does the area around my structure look like, to kind of determine how exposed it is.
Yeah, let's start hitting those factors. So the one you're getting at there is probably the topographic factor, I imagine, but that also kind of includes surface roughness. You're more saying surface roughness. So yeah, depending where your building is located, you can have it, let's say, in some salt flats, surface roughness D, flat, unobstructed areas and water surfaces. So there's some distance to this, which I don't. Do you recall what this is? Like how much flat you need to call it D?
Oh man, I believe it's 2,000 feet.
Sounds about right. And then moving down the line, surface roughness C, we have relatively open terrain, scattered obstructions, and a lot of codes will default to C, which pretty much covers anything around town. D is really, it's got to be a long distance of open field. I know I've looked, at a farm in eastern Colorado, and we still ended up using C. It just wasn't completely open for far enough. It really takes a lot. Most buildings you do can be B. And I know we generally default to C. You're safe with C. But if you're doing anything in a city, you can go down to B and get that reduction. And then the other thing you've got is your topographic effects. So this is, these are your hills, basically. So when wind approaches a hill, it basically gets squeezed by the land and it has to accelerate. So it's just like a venturi, or, which is the throat of a carburetor or something. I know these terms, but, from water class in school, if you took this, as water goes through constriction, it has to speed up, right? The pressure reduces, but the speed increases. So if you put your building on top of a hill, you're basically putting it in the center of one of these venturis. So the wind speed will increase quite a bit at the top of the hill.
Now, something interesting, Max, that you may or may not know is there's a minimum you have to keep.
Tell me more.
I think you know enough. Yeah, so if you look in the code, when you go through these equations, you can get them to pop out some pretty small numbers potentially. If you really have a perfect site, let's say, that gives you the best factors through everything, and you're at a super high altitude even, you could get the pressures on your building to be crazy low, but the code requires at least a minimum to be specified for design, and that would be a 16 pounds a square foot for your wall pressure and a roof pressure of 8 pounds per square foot. So there's, you're trying to get fancy over here, taking all your factors and your wind reduction due to altitude, but you know what? We're going to stop you at 16 and 8.
And those are ultimate loads, right? Yeah,
sure.
So we're in 710. Those are ultimate. And in 705, that minimum was 10 PSF. And it was actually 10 all around, I believe. So now we've got this distinction, 8 and 16. All right, let's hit some more factors here. I think we just have 2 more. The one that I really like is directionality factor. It doesn't change very often. This is that 0.85 in your equation. That's probably just repeated all the time. But what it's looking at is the probability that your building is hit with a wind in the exact direction that it is the worst. So, if you have a gable roof, let's say the broadside of a barn here, what's the odds that the wind comes directly orthogonal with the long side of the barn and is the absolute worst case? It's not very good, right? So they apply this directionality factor to adjust for this probability, and this is typically 0.85 for a building main wind force resisting system. It's always 0.85.
Whoa.
Yeah. If you're looking at some other weird stuff, so based on that example there, if you had something that was round, a round chimney or tank, the odds of the wind coming at the worst direction are pretty darn good because it's the same shape all around. It is round. So your directionality factor there is 0.95. It's very nearly certain that you're getting that worst case, except there will be some angle to it, And then this jumps around. A truss tower with any cross section other than triangular, square, or rectangular, I can't think of any others, is 0.95.
Now, something you just said there, main wind force.
I guess we didn't really define that.
What does that mean?
I mean, I think it's a pretty good description of itself, but usually in
what
the
else
code,
is there?
It's almost always written as MWFRS. And this is your shear walls or whatever. This is your main structure that resists your wind force
So maybe you could define it as the same elements that would resist your seismic loads.
Yeah, I was about to, and then I was like, well, there's wind in the title, so that's kind of weird, but it is the same elements, absolutely. Yeah, it is your main wind and seismic force resisting system. The other version of this is your components and cladding. This is everything else. Oh, and so component and cladding loading, that's a higher wind pressure. Is that right, Zach?
Sure.
That's exactly right. So when we're looking at components and cladding, we're looking at a smaller pressure. And the way that higher pressure, smaller area. The way I always think about this is if you're looking out over a lake and it's windy, right? You see the lake, the water in the lake kind of move in little patterns. It's not all at once. So when we're looking at the main wind force, we're assuming that all this wind is uniformly hitting the building. But if you kind of zoom out, there's these pockets of high and low pressure. So when you look at a smaller area, you're more likely to get this lower pressure, but you're also more likely to get these higher pressures. So you can end up with a higher average pressure than you would when you're looking at a large area. And the cutoff they use is 700 square feet. So anything below 700 square feet, you can get into your CNC loading. It's going to be a higher load. And until it gets, past that 700 size, then they say, it's uniform enough. The wind is not completely uniform across a cross section of the wind, but it's close enough at that point.
So I'll design my shear walls for my main wind force system, resisting system force. And then I'll design the studs in those shear walls for that wind pressure of the components and cladding.
Absolutely. Yeah, and I've even seen, I don't know if this holds, this was a while ago, that you don't have to use component and cladding loading once you're to this like second degree member. So let's say, this is a bad example because it's on the ground, but if you had a floor joist and a girder, your floor joist would have this CNC loading, but your girder wouldn't have. Okay, I think we got one more to go over, and then we'll do our second part sometime in the next week or two. The last one we got here is the enclosure classification. There are 3 enclosures in ASCE 710, and I'm pretty sure now there's 4 in ASCE 716. Okay, so what we're going to look at now is enclosure classification. In ASCE 710, there are 3 categories of enclosure. You can have an open building, like a picnic pavilion or something. You can have an enclosed building, pretty much any house, or you can have something in between. That's a partially enclosed building. An enclosed building is actually something, it's defined as a building that does not comply with any of the other 2. An open building is pretty obvious. It is each wall having at least 80% open. And then the one that's actually kind of complicated is this partially. So partially enclosed building is a building that complies with both of the following conditions, being the total area of openings in a wall that receive positive external pressure exceed the sum of the area of the openings, blah, blah, blah. This is actually kind of long. I don't think it's fun to read. But basically, it's somewhere in between, right? So the reason that this is worse, right, you have a higher pressure in a partially enclosed building. Your internal pressure coefficient is 0.55 because this thing can basically be inflated without room for the air to blow out. An open building, fills up with air and just comes on out the other side. If you have a partially enclosed building and it's blown from the wrong side, you can have this sort of fill up like a sail and kind of get double your wind load. You still have positive on the walls, you still have negative on the backside, but now you've got this giant positive on the inside as well. So that's really your worst case.
Right. Yeah, it brings us up to 0.55 from 0.18.
So that's I think it. On the basics of wind, looking at all the factors and kind of the intro here, I think
we got
it covered.
You're right. They did throw in a new enclosure classification of partially open structures. That's right. They found that it was too conservative to be either partially enclosed or an open structure. And so they found that there's a lot of buildings that fit into this kind of middle ground. And so in ASCE 716, they added in a new classification.
And thank you, the audience. If you enjoyed the podcast, please subscribe. It helps us out a lot. And if you have any questions, shoot us an email. Email and every contact is in the show notes down there.
And before we sign out, I want to thank everyone that's listening right now. We've been getting a lot of feedback, both email, Facebook, Instagram. The show's really getting a lot of feedback from people, and I think that's awesome. Both, criticism on how we can do better and people liking some of the things we're saying. So please keep it coming, and our audio is getting better every week.
We're working on it.
We are working on it. So let us know what you guys would like and what you look forward to and what you don't like, and we'll
we got some ideas for shows from people coming in on email and Instagram and stuff, so we really appreciate that, and those are in development.
So reach out to us and have a good week.
See ya.